This video is an introduction to some basic ideas about estimators and sampling distributions. So a running example we use throughout some of these slides involves estimating the unemployment rate in the U.S. So in the U.S., we have the Bureau of Labor Statistics that reports on estimates of labor force statistics, including the unemployment rate. And what they do is they divide the adult, civilian, non-institutional population into three groups. So everyone's in exactly one of these categories conceptually. Employed, which is what you think it is. Unemployed, which recall in economics means, it does not mean not employed. It means not employed and actively looking for work. Okay, and then everyone else is not in the labor force. So this would be retirees, stay-at-home parents, many full-time students, etc. All right, the labor force is these first two groups, the employed and unemployed. And the employment rate is the share of the labor force, employed plus unemployed, that is unemployed. Okay, and whatever that underlying unemployment rate is in the population, I'm going to call that mu. Okay, and to learn about the unemployment rate, every month in the U.S., the Census Bureau fields the Current Population Survey, or CPS, where they talk to about 60,000 households each month to learn some basic things, including the employment status of the adults in the household. All right, this is from the most recent BLS report as of the time I made this video. This was released in early September and applies to August data right here. So it's formatted a little strange, so you can see comparisons to previous months and a year ago, but the most recent data here is all the way on the right. And all the numbers here are in thousands. Okay, so the way to read this is 274 million in the population of interest. That's the adult, civilian, non-institutional population. 163 million-ish employed, 7.4 million-ish unemployed. And so the unemployment rate is the share of the labor force, which again is that unemployed, employed added together right here, 171 million or so, the share of that is unemployed. And it worked out to about 0.043 or 4.3%. Okay. So that's where those unemployment numbers are coming from when if you see a news report about the monthly jobs gains and loss, that's actually come from a different data set, and then the estimated unemployment rate comes from the CPS. Okay, so the underlying population, there is some true unemployment rate for August 2025 in the U.S. We're going to call that unemployment rate mu. This is an example of a parameter of interest. It's a fixed, at least for a point in time, okay, but unknown numeric characteristic of the population. The 4.3% estimate that we got, or as a proportion, 0.043, that's an estimate or a point estimate of that parameter, okay? It is not, almost certainly, it is not the actual unemployment rate in the population, okay? Our estimate would not, in general, be equal to the underlying parameter value, okay? Because we didn't observe everyone's unemployment status. We observed a large sample from the population, but not the whole population. So a lot of the slides here are about an idea that's that can be difficult to grasp, and that's the idea of an estimator. All right, an estimator is, one way to think about it is, it's a function for computing point estimates from data. Okay, so how did we compute the unemployment rate for August 2025 from the CPS? What we did is everyone in the labor force is either employed or not, is either unemployed or not unemployed, 1 or 0 for computing the unemployment rate here. And so every single person, if there's tens of thousands of people here, these variables are going to resolve to 0 or 1 according to whether the person's unemployed or not. All right, and we're just going to take the average. Just adding up all the zeros and ones will count the number of people who are unemployed, and then we'll divide by the number in our sample, and that will give us an estimate of the unemployment rate. All right. When we talk about an estimator, we're thinking about this process from the standpoint of before we take the random sample in the first place, okay? So if we had taken a different sample instead of the 60,000 households we did survey in August, if we had taken a different sample, then the number of people who were unemployed would probably be slightly different, and our estimate of the unemployment rate would be slightly different, okay? So person 1 in our sample, who's in the labor force, right? Are they unemployed or not, 1 or 0? Well, across different samples, we could have different answers to that question. In some samples, the first person we talk to would be unemployed, and in many samples they wouldn't be. So if X1 stands for the unemployment status of the first person in the labor force we talk to, that's a random variable. Okay, and all of these actually are random variables, and therefore the sample mean or sample proportion in this case is also a random variable. Okay, so estimators look like just the formulas for computing statistics, but when we talk about them as an estimator, and you can see it reflected in the sort of capital letters that are used here, we are thinking of them as random variables from the perspective of before the random sample is taken. Okay, you can see some common notation here. I'm starting with this one just because it affords clear distinction among parameter, estimator, capital letter, point estimate, lowercase letter. Okay. Going forward, you might see in this example, we might instead say, it's the unemployment rate's the proportion of people who are unemployed. So the population version is this, and then the estimator or the point estimate would be little p hat, and you would just have to know from context whether we're thinking of a particular value or an estimator idea. Okay. All right, a couple more things here real quick. Because the estimator is a random variable, that is, we can get different estimates from different random samples, there's a whole probability distribution of values that we could get for our estimator, okay? And that is called a sampling distribution, right? And you can take this idea all the way back to the very beginning of our study of probability. There's a notion of an underlying probability experiment or random experiment, and here that is the process of taking a sample from the population. Once you take the sample from the population, everything that happens after that is just data analysis, right? Like the numbers are what they are, and there's no randomness to it once you've picked your sample, okay? The thing that generates the randomness in the random variable is the idea that you could have, in principle, selected a different subset of the population to be in your random sample, okay? So an estimator, like our sample mean, is a random variable. All right, the randomness is across possible samples, an idea that's really important, which is why I keep repeating it. The distribution, the probability distribution of the estimator is called its sampling distribution. And just like any distribution for any random variable, it has a mean and it has a standard deviation. One property we could hope to have is that our estimator is what's called unbiased. That is, if its mean is the population parameter of interest. So here theta is the population parameter, and theta hat is our estimator of that parameter. Okay, so a sample mean, x bar, is unbiased if its mean is the population mean mu. All right, and what is it? What are we saying if we say the mean of the sample mean? All right, remember, this expectation is being taken across possible samples. So we're accepting the fact that sometimes our unemployment rate estimate will be too high and sometimes it will be too low, but we're hoping that across all the possible samples we could have taken, at least the average of the unemployment rates that we would have gotten is equal to the underlying population unemployment rate. That's the idea of unbiasedness. We're going to assume throughout here that we're doing what's called simple random sampling, which I'll typically just refer to as random sampling. You can see the technical definition of it here, but basically it's what you think of random sampling as being. You reach into the population and randomly draw someone to survey. You reach back in and randomly draw a different person to survey, and so on. Okay. Under simple random sampling, the observations to be obtained from your sample, okay, are independent and identically distributed. And this is often shortened IID, but I really want you to sort of understand what these things stand for and why they work the way they do. So let's start with the independence. The independence means the value of x sub I is not informative about any of the other x sub j. So just to put specifics on this in the unemployment rate example, knowing whether person 1 in your sample is unemployed is not informative about whether person 10 is going to be unemployed or not, because these are independent observations from the population, and that's because of random sampling. Okay. The random variables are identically distributed, and that's because every time we reach into the population and randomly survey someone, we could get anyone from the population, okay? And so the distribution of X sub 1, our first observation, is the population distribution of employment and unemployment, for example, among people in the labor force, okay? So each of those random variables has the population distribution. That's what the identically distributed thing means. There are definitely other valuable ways to survey, right, in certain situations, but we're not going to get into detail on those. We'll assume random sampling.